Okay, good evening, students. This is the short lecture on impedance. This second class on impedance. Um, so, yesterday's class we looked at impedance is defined as this delta V by delta I. For a simple resistor, impedance is R the magnitude of the resistance. And for capacitor, because we need to include also the phase information, so we will represent the impedance from the capacitance or inductance as a imaginary number. So I use j is equal to root minus 1. So let us take a circuit like this where you have an impedance, where you have a resistance R in series with a capacitance. So that impedance from this part is Z1, impedance from this part is Z2. So the total impedance is the sum of these two impedance. So if I look at that circuit like this where the resistance is in parallel to the capacitance, so the corresponding impedance looks like this. So in such a circuit, the admittance add, that means the inverse of impedance. So 1 by Z1 plus 1 by Z2 is the admittance. So inverse of it is the impedance of this circuit. Okay. So let us take the circuit for a while, discuss about this. So the total impedance of the circuit can be written as Re, the resistance of this part, plus 1 by j omega c. This is the angular frequency. And if I multiply by j, both numerator and denominator, so this transforms something like this. This is a real part of the impedance, and this is the imaginary part that comes from the capacitor. So as we discussed yesterday, if the frequency goes to infinity, okay, so this term will disappear. What does it mean is the capacitor act like a short, so the current will go through this, and this will be simply like an wire that is here, which has zero potential drop. And suppose if the frequency goes to 0, that means you apply a DC potential across this because there is no AC component when the frequency is 0. Then what will happen? Quickly this capacitor will get charged in a fraction of a second. After that, this will act like an open circuit. The resistance of this part will become infinite. So no current will flow in the circuit. And let us look at this circuit wherein we have an RC in series with the RE. This is a scenario in case of a single electrode electrolyte interface with the solution resistance. So this is how you write the total impedance of this circuit that we discussed earlier. If the frequency is 0, that means you simply apply only the DC potential. What happens? The capacitor, when you will quickly get charged in a fraction of a second, then all the current that you apply will choose to go by this. Whereas in the previous circuit, when R and capacitor were in series, there was no current flowing. The flow was blocked. But here, since you have a two path for the flow of current, even though this get completely charged and oppose any flow of current can still pass through this. Okay. So suppose if you go to a very high frequency, for example, before that, so when the frequency is 0, there is no AC component, so only DC component, so the current goes through this. When the frequency is very high, and this will act like a short for the AC component. That means for the AC current, which is a result of a change in the amplitude of the voltage, okay, that will pass through this, but the DC current will continue to pass through this. So, okay, so the impedance that you see is due to that AC component. That's what you would see. Okay, but remember, if we are using this circuit, I mean simulating this circuit as the electrode electrolyte interface, what you should remember this RT, which is a function of our potential. That means if it would have been a solid state circuit, irrespective of what is the DC potential you apply, there won't be any change in the impedance, total impedance of the circuit. Whereas if it's a real electrochemical system, since RT will change as a function of our potential, so this would give a different impedance at different DC potentials. Okay, so the current at zero frequency will pass through both the resistor Re and RT. Current at high frequency will pass through only through Re. That is the AC component. The DC component still will go through Re and RT. And we can represent this real impedance and imaginary part of the impedance like a complex number, and this can be represented like this. So this is your real part, and this vertical line is the imaginary part. The magnitude of this can be read from the y-axis, and magnitude of this can be read from the x-axis. Okay, so imagine now if phi is 0, that means the phase difference between the voltage waveform and current waveform is 0, that's something like a resistor. Then this vector will lie on x-axis. Then you have only this radius as the impedance of your circuit, which is nothing but the resistance of the resistor that is there in your circuit. Suppose if you have a phi as 90 like in a capacitor, then this vector will be along the y-axis. Then the real component will be 0, so your imaginary component will be whatever the value that is here, which is equivalent to again now the radius of this circle. Okay. So this is what I have written here. So in general, we can write this as the impedance as this is the magnitude of the impedance, this is a mod of C multiplied by e power j psi. This e power I theta, how do you write? Is a cos theta plus I sin theta. So you know that at frequency 0, your Z will be equal to, impedance will be equal to Z itself. Why? Because at psi is equal to 0, this is cos theta plus I sin theta, so the sine component will be 0. So we have only cos component that is coming from the circuit. Okay, so and then at psi is equal to 5 by 2, you will have Z will be equal to J times of the total psi. This can be the impedance value can be written as root of real part square plus imaginary part square. As I told you, the real part of the impedance nothing but the total impedance Z, okay, magnitude of that, which again depends on the frequency whenever you have elements like capacitor and inductor, and cos theta, that is psi, which is a function of frequency. Okay, so similarly you can write an expression for the the imaginary part of the impedance. This is nothing but cos theta as CR minus ZW. So that is what you see in this drawing. So the cos phi will be this magnitude divided by this. So this magnitude is the real part, and this is the magnitude of this vector, which is C. That's the total impedance. And we can look at uh, the Bode representation of I think we have stopped our class somewhere here, I believe. Yeah, okay.